In the previous video, we discussed how the Kruskal algorithm works. So in this video, we are going to discuss how we can actually implement it conceptually. So last time we discussed like we need to sort these edges, which should be pretty straightforward. Like if we were to use a edge list kind of representation of our graph, you can easily sort them. Even if you are using like adjacency lists, there are mechanisms to sort them. So that's not the interesting part. But typically, Kruskal's algorithm is requires you one other thing, which is you need to keep adding edges till there is a cycle in the graph. So we cannot accept any cycles in the minimum spanning tree. So the question you might be asking is how can we detect cycles? Okay, when we add an edge to our minimum spanning tree. So the first idea here is to create a set. Now, if we create a set such that like whenever we have an edge, we add both these vertices to the set, and whenever we add another edge, we basically check if these vertices are there in the set or not. Like if both of them are in the set, you don't add a new edge to the minimum spanning tree. But if either of them is not there, then you can connect it. Now pause the video for a minute and think about like what might be a case where will this ever work, or is there a case where this won't work? So the correct answer is this won't work because we discussed this idea of connected components. So I'll give you an example. We are going to cover an example of why this will not work, which is this will not work when we have two disconnected components. So let's see a quick example of what I mean by that. So in this case, like let's say if we maintain a set, initially we have add like 0 1 to this set. So 0 2 is added to our minimum spanning tree. So that's why we add 0 2 to this set, because we have 0 and 2, and we add it to the set. Next, we add 3 5. So if we add 3 5 to the set, because it's not creating a cycle. Now, if we try to add 0 3, since 0 and 3 are already there in the set, the issue is we are going to ignore this, because if we are trying to detect a cycle using this mechanism, since both of them are already in the set, this is not going to work, because it will say that 0 and 3 are already there in the set and it's going to create a cycle. So this approach doesn't work in this case, like of disconnected components, because the set won't be able to figure out whether the components are connected or disconnected. So we are going to discuss like these numbers like 0 3, the edge 0 3 or 0 2 is already connected, but if there was something like 3 2 or 5 2 or 5 0, in all those kinds of edges will never be picked in the minimum spanning tree if they are already there in the set. So this brings us to the second approach, which is a correct approach, but it's computationally more expensive. So we can detect a cycle by using DFS. We are going to discuss like how to detect cycles using DFS in the next problem solving lecture. But the key idea is like if you have a node, you start with that node and start a DFS. Like you keep going. If at any point you are going to see that node again, which is you come back to this node, that means there's a cycle in the graph. If you do not see the predecessor node, that means there's no cycle in the graph. In case of cycle detection using DFS, you need to ensure that, like, let's say if you go from 1 to 4, you have to make sure you are not considering 1 to 4 as a cycle. And what I mean by that is you need to make sure that the parent of 4 is not its neighbor, not 1, but any of the predecessor nodes that you saw before. So to keep a track of that mechanism, we are going to use like either BFS or DFS by keeping a track of who is its exact parent or who is its adjacent parent. We are going to discuss that in the problem solving lecture, but you can tweak the DFS algorithm, which we already discussed that had a complexity of of v plus e to detect a cycle in the graph. Now, since we are adding this for every edge, after every edge, we are going to call this method of detecting cycles. This total complexity of this would be something like of e into v plus e, because there are e different edges. Now, this is computationally very expensive because e can easily be equal to v square in terms of like if you have a dense graph. So this kind of like simplifies to ev plus e square, and since we know that v will be less than e, this is technically equal to o of e square. So this brings us to the third approach, which is called the disjoint set approach. We haven't discussed this data structure, and a lot of classes actually they go over this data structure in depth. We are going to go over this in your discussion sections. I've asked your TAs to go over this, but conceptually we are going to discuss like how this works, so you can implement this later on in your discussion sections. So this disjoint sets idea is the idea that like we have a group of sets instead of just one set. And this disjoint set data structure, it's also called weighted union disjoint set data structure because there are different types of disjoint sets. In this case, since the edges are weighted, we are going to use that. And this data structures you has two different operations. The first one is the find operation, which identifies like if I provide you a vertex like 0, which set is this vertex in amongst all the other sets. So we have a group of sets. So the find operation finds whether I is in this set, or which one. Okay. The union operator. Now, another thing to note is, let's say if you have vertices in these individual sets, every vertex will be just once in a set. Like it cannot be that one is in this set and one is in another set. So each vertex is in just one set. The other operation is the union operation. And what this one does is it merges two sets that contain I and the set J. So if I provide I and J, let's say if you have a set of sets that have 1, and then there's another one like 2 and 3, and if I perform a union operation with the value 1 comma 3, it's going to merge these two sets. Now there'll be just one set, which is 1 2 3. So you can represent all the disjoint components. Like in this case we had like when we were walking through that problem, we saw that there were two disjoint components, like 0 2 is one component and 3 5 is another component, and each of the disjoint components or disconnected components are represented by one set in the sets in a group of sets that belong to the disjoint set data structure. Another thing is a cycle is created by adding an edge for which both vertices are in the same connected components. So let's say if we have a set of components, like in this case 0 and 2 and 3 and 5, if we try to add 2 and 3 to like this data structure, we can just like merge these sets to create one set. But now, if we try to add 0 and 3, since 0, 2, 3, 5 are in the similar set, they, if we try to merge 0 and 3, then it will say that it's a cycle. We are going to see conceptually how this is working. And just to iterate, like the complexity of this disjoint set data structure, like if you use a disjoint set to compute the Kruskal's algorithm, this can give us a better complexity, which is O of E times log V, which is much better than O of V square, which we saw, E square, which we saw earlier for the second approach, although both of them are correct. So how this works is we choose an edge in this Kruskal's algorithm. Now we use the find operation, which is if find of I and is not equal to find of j, then we union both the sets. So what I mean by that is we'll start the algorithm in which there's v number of sets. Each set represents one vertex of the graph, such that like each set has just one member in that, which is the vertex of the graph. Now we are going to choose the first edge. Like again, it's in ascending order. We are now going to see whether 0 and 1, in this case it's 0 and 2, so 0 and 2, are they in the same set or not? Since they are not in the same set, we are going to union them, which is now the next step would look something like this, which is 0, 2, and then 1, and then 3, and so on, like 4, 5. Like there'll be those sets. So you can see it looks like this, and we have added this set. Next, we have 3, 5. So what we essentially do is we check where is 3 located. So 3 is in this set. Next, we check where is 5 located. 5 is in this set. Since they are in different sets, we can union them. So the next iteration would look like this, which is 0, 2, 1, 3, 5, and 4 as a separate set. Okay. The next one we have 0, 3. Now here we can see that it's not creating a cycle. And in the earlier approach, when we had just one set, this was not being added. That was the issue. So here we see that 0 is in this set while 3 is in another set. So the find operations will reveal two different sets. So the union will be successful. And now we have 0, 2, 3, 5 in one set. Another set will be 1 and another set will be 4. So in this case, all of these numbers in a set represents a connected component. Next, we are going to see, like this is our input to the next iteration. We are going to see 1 and 2. So for 1 and 2, we can see that 1 and 2 visually is not creating a cycle, and 1 is in this set and 2 is in this one. So again, we are going to merge them, which is now our set would look something like this: 1, 2, 3, 5, and then 4 will be another. So again, just a reminder, we'll stop when this set or one of the sets is the size of the disjoint set is just one set that contains all the vertices. So we add 1, 2. Next, we have this 2, 3. Now 2, 3 will create a cycle. Like you can see here. Here, it will find where 2 is. So 2 is in this set. And then it will find where 3 is. And 3 is also in this set. So the union operation will not be performed because the if condition is not satisfied. So this won't be added to our disjoint set. Similarly, when we have like 2, 5, 2 and 5 are again in this set. So this won't be added. Next, we have 0, 1. So 0, 1 is in this set. It won't be added. And finally, when we have 1, 4, 1 is in another set. Like you can see, 1 is in this set, 4 is in another one. So you merge these two and you add this to the minimum spanning tree. Now, one thing to note here is that this disjoint sets can be actually implemented using arrays, and I'm like we are going to cover that in one of the discussions because that's like another whole lecture, so I don't want to cover that in the lecture. But if you are curious to know how these are implemented, we are going to cover that in the discussions. But for the sake of the exams, you won't be asked like how to implement disjoint sets, but there's a stepping exercise that covers Kruskal's algorithm. And if you follow the first approach, which is if you follow a one set approach, that's not going to work because we have some test cases that are testing whether you have built a disjoint set or you are solving the cycle problem with the help of DFS. You can implement it either ways. One is computationally more expensive, other one is less. So, and it's a more efficient solution. In the next video, we are going to discuss topological sort.